Hello, welcome everyone. In this lecture, we're going to solve few more questions on per unit system, insulators and distributors. So the first question is, an isolated synchronous generator with a transient reactance equal to 0.1 per unit on a 100 MVA base is connected to a high voltage bus through a step-up transformer of reactance 0.1 per unit on a 100 MVA base. The fault level at the bus is. So in this question, what he is asking, generator which is connected to a bus through a step-up transformer, and this is the bus which is specifying. So he is asking what is the fault level at this bus. So to calculate the fault level, we have to simulate three-phase short circuit fault. Understand? So he has given the per unit value of the generator and the step-up transformer. Both value are 0.1 per unit on a same 100 MVA base. So if you draw the per unit impedance diagram, so it will become what? This is the transformer and this is the short circuit. So generator voltage we write as 1 per unit and generator reactance is 0. Per unit. The transformer reactance is 0.1 per unit. Now, what is the per unit fault current in this situation? Per unit fault current is equals to divided by 0.2, that is 5 per unit. This is 5 per unit. So fault level is nothing but short circuit MVA for a given fault. What is our fault? To calculate the fault level, we have simulated a three-phase short circuit fault, for which initially we have calculated the per unit fault current. The short circuit MVA for a three-phase fault is given by base MVA into IF per unit fault current. So what is our base MVA? Since both the machines are having 100 MVA base, so obviously our base MVA for the given problem will become 100 MVA. And what is our per unit fault current? It is 5 per unit. So the overall short circuit MVA will become how much? 500 MVA. So if you simulate a three-phase short circuit at any point in the power system network, you will get the fault level or short circuit fault level at that particular point. Okay, here in this question, the answer is 500 MVA. So he's telling that there is a power transformer. So this is a LV side is 11 kV, HV side is 400 kV, and the transformer MVA rating is 200 MVA. So in a transformer, the per unit impedance is calculated for the equivalent impedance referred to either primary side or secondary side. That means first we will calculate the equivalent impedance of the transformer on HT side or LT side, and we calculate the per unit value for it. So in a transformer, the LT equivalent per unit impedance is equals to HT equivalent per unit impedance is same, that is treated as the per unit impedance of the transformer, whose value in the problem is given as 0.05 per unit. Since in most of the power system element we only consider reactance, so all the value or all the impedances are only reactances. Now, so the equivalent impedance, the equivalent per unit impedance referred to either primary side or secondary side is same, whose value is 0.05 per unit in this case. Now, to calculate the question what he is asking is to calculate the equivalent impedance referred to HT side. So what will be this value? Per unit equivalent impedance referred to HV side and the base impedance of HT side. Understand? So actual value equal to per unit value into base value. So what is the per unit value? J 0.05 per unit, and to calculate the base impedance on HV side, what is the formula for base impedance? V base HT side base voltage square divided by S base. Okay, so this value will become J 0.05. What is the base voltage on HT side? 400 kV. 400 kV square divided by what is the base impedance of the transformer? 250 MVA. So this value will become J 32 ohm. So the question is the actual leakage reactance of the transformer referred to secondary side of 400 kV. The value is 32 ohm. When a three-phase balanced star connected source is supplying a three-phased balanced star connected load, then there are four options. Load neutral and source neutral are at zero potential and neutral grounding impedance is considered for per phase analysis. Load neutral and source neutral are at zero potential and neutral grounding impedance is neglected for per phase analysis. Load neutral and source neutral are at different potentials and neutral grounding impedance is considered per phase analysis. So the fourth option, load neutral and source neutral are at zero potential and neutral grounding impedance is considered for per phase analysis. So it is a theoretical question. If you know the fundamentals of power system, you can easily say, so when you supply a when a balanced three-phase source is supplying a balanced three-phase load, then we already know that the potential of all the star points in the power system network is zero. Either it is a source neutral or load neutral or the neutral of any star connected transformer when a power system is operating under balanced condition. That is when a balanced three-phase source is supplying energy to the balanced three-phase load, all the neutral points are at a zero potential. What is the potential of the ground? Potential of the ground is also 0 volt. So if you connect the impedance, any impedance between source, so if you connect any impedance between the source neutral point and ground or the load neutral point or ground or any neutral point and ground in a balanced three-phase power system, there won't be any current flowing through that because both the neutral point and ground are at same voltage, that is 0 volt. So between two equipotential points there will not be any current flow. There will not be any current flow. So when an element is not carrying any current, it can be treated as a open circuit. So we need not consider the neutral impedances in a balanced power system, whether the impedance is connected between the source neutral and ground, between load neutral or ground, or between any neutral and ground. The impedance need not be considered if the three-phase power system is operating in balanced condition. So what is the option? So in this case the option is load neutral and source neutral are at zero potential and neutral is neglected per phase analysis. So option B is the right option. Option B is the right option. Next, the fourth question is, Capacitor absorbs lagging reactive power and delivers leading reactive power to the power system, and inductor delivers leading reactive power and absorbs lagging reactive power, and so on and so forth. So by permutating, he has the 4 conditions. So he is asking the basic concept of how capacitor and inductor behaves. So capacitor is an element when you apply voltage across it. Capacitor is an element when you apply voltage across it. It absorbs minus Q. Minus Q means leading reactive power. Minus Q means leading reactive power. Plus Q means lagging reactive power. Okay. So capacitor is an element that absorbs minus Q. Capacitor absorbs minus Q. Inductor is an element when excited it absorbs plus Q. Inductor is an element when you excite it with voltage, it absorbs lagging reactive power. So if you understand this basic concept, but how actually we treat it in power system? In power system analysis, we treat inductor as an element that absorbs plus Q, capacitor as an element that supplies plus Q. That means inductor absorbs lagging reactive power, capacitor supplies lagging reactive power. So this convention will usually is in the power system analysis. So considering this, what is the right option? So we can treat inductor as an element that absorbs positive reactive power, or the element that supplies negative reactive power, or capacitor as an element that supplies positive reactive power or absorbs negative reactive power. Usually in power system analysis, we follow this notation. We treat capacitor as a supplier of positive reactive power, inductor as an element which absorbs positive reactive power. So from this, what is the right option? Inductor delivers leading reactive power and absorbs lagging reactive power. Capacitor absorbs leading reactive power and delivers lagging reactive power. So which two are correct? Option 2 and option 4 both are correct. Option C is the right option. Is in per unit representation of transformer, the base voltages on either side of transformer will be in the ratio of. So while deriving the per unit representation of a transformer, the basic idea with which we start the analysis is that the base voltages on either side of the transformer must be in the ratio of their line to line transformation ratio. So option A is the right option. VB1 by VB2 should be equal to, the transformation ratio is N1 by N2 or V1 by V2. Next question. 4 alternators, each rated 5 MVA, 11 kV with 20% reactance, are working in parallel. The short circuit MVA at the buses. So what is telling? Four alternators with identical ratings are connected to a bus. So what is the fault level of that bus? Again, drawing the per unit impedance diagram for this given system, we are going to have So this is the per unit impedance diagram for the given system. So to calculate short circuit MVA, we have to simulate which fault? Three-phase short circuit fault. We have to simulate three-phase short circuit fault. So to calculate the fault current, we have to Thevenize this per unit impedance diagram between the bus and the reference. So if you calculate Thevenin's equivalent of this system, what you are going to get? The Thevenin's equivalent value is going to get So if you Thevenize between the bus and the reference, you're going to get this circuit. Now the IF per unit will become how much? IF per unit, if you only want the magnitude, this value will become 1 divided by 0.05, that is 20 per unit. Now what is the short circuit MVA? Short circuit MVA or fault level is given by base MVA into IF per unit for three-phase short circuit fault, whose value boils down to 20 into what is the base MVA? 500 MVA. So the short circuit level, the short circuit MVA at the generator bus bar, which is having 4 identical generators connected to it, boils down to 100 MVA in this case. Understand? Next question. The non-uniform distribution of voltage across the units in a string of suspension type insulators is due to. That means why, in this question what he is asking, why the voltage across the string of insulators is not identical. That is, this voltage is different between this voltage. That means the voltage across the each disc are different. That is why. What is the reason for this? That is the question. Here all the discs that are used in the string of suspension insulators are identical. All the discs are identical. They have same impedances. That means the impedance of each disc is same. Okay. Now from the conductor that is connected to the last disc, the current will flow through all these capacitances. So these currents that are flowing through the discs are different. See, you can observe the current flowing through the disc that is connected to the conductor, it is I3. Next, the current flowing through the other disc is I2, and the current flowing through the disc that is connected to cross on is I1. Since the discs which are having identical impedances are carrying different currents, so the voltage across these discs are different. Why the currents are different? Because there is a leakage current that is flowing through the air. There is a leakage, capacitive leakage current that is flowing from the metallic pin junction between two discs to the tower. There is a leakage current, capacitive leakage current that is flowing from the metallic pin junction to the tower. This is the reason. So these currents, these capacitive leakage currents in this diagram are designated as I3, I2 and I1. Because of this leakage currents, the currents through the discs are different, so they are having different voltage drops across them. So what is the reason? What is the reason? The non-uniform distribution of voltage across the units in a string of suspension type insulators is due to the existence of stray capacitance, between metallic pin junction and the tower body. Because of this existence of the stray capacitance, there are some leakage currents flowing from metallic junction to the tower body. Because of this leakage currents, the current distribution through the discs in the suspension type insulators is different, and thus they are having different voltage drops. Consider a 3-phase 50 Hz 11 kV distribution system. Each of the conductor is suspended by a string of two identical ports in insulators. The self capacitance of the insulator is 5 times the shunt capacitance between the link and the ground. The voltage across the two insulators are. So here he has given the equivalent circuit of a suspension type insulator that has two discs. So this is and he is asking the voltage across the individual discs. The line to line voltage of distribution system is 11 kV. So voltage of conductor with respect to tower, that is voltage of the conductor with respect to ground, is 11 by root 3 kV. Okay, now this 11 by root 3 kV is distributed across the two discs. The distribution we need to find out. Assuming current flowing through the first disc that is connected to the conductor, be I1. The current flowing through the second disc that is connected to the cross arm be I2, and let this current that is flowing through the capacitance C is IC1. Now, what is by the KCL at the node, we are having I1 is equals to, so I1 value we can write it as E1 divided by, what is the impedance of this 5C capacitance? 1 divided by j omega 5C. Similarly, I2 how we can write? E2 divided by 1 divided by j omega 5C. And what is IC1? See here at this point, what is the voltage with respect to ground? This point voltage is E2. With respect to ground, this point is having a voltage of E2. So it will become what? E2 divided by 1 divided by j omega C. So if you simplify this, what you're going to get? J omega 5C E1 is equals to j omega 5C E2 plus j omega 5C E2 divided by 5. I am multiplying and dividing with by 5. So if you cancel the terms, what you're going to get? If you cancel j omega 5C in all of them, you're going to get the relation E1 is equals to E2 plus E2 divided by 5, which implies E1 is equals to 1.2 E2. Now, what is the voltage of the conductor with respect to tower, which we have already calculated? The voltage of the conductor with respect to tower or ground is 11 by root 3 kilovolt. So this value is equals to how much? This value is equals to E1 plus E2. So by solving this one, 11 by root 3 is equals to, instead of E1 I am substituting 1.2 E2 plus E2. So from this you are going to get E2 value is equals to 11 by root 3 into 2.2. So this value is how much? 2.89 kV. So this is E2. What is E1 value? E1 value is equals to 1.2 E2, this is 1.2 into 2, 3.46 kV. So E1 value is 3.46 kV, E2 value is 2.89 kV. So what is the right option? B is the right option. So next question. A DC distribution system is as shown in the figure with load currents as marked. The two ends of the feeder are fed by voltage sources such that Vp minus Vq is equals to 5 volt. Find the current supplied by sources at P and Q respectively are. So in this question, it is a DC distributor which is fed from both ends. That is, there is a source at point P and there is a source at point Q. So both these sources are feeding this distributor which is having 4 loads. What is the total load on the distributor? The total load on this distributor is the sum of all these load currents. This value is how much? 75 ampere is the total load on the distributor. So to approach this kind of problem, we have to assume the current that is being fed from the source at P. Let us call this current as, say, I. This current is I. So what will be the current that will be fed from the source at Q? The remaining current. The remaining current is how much? 75 minus I. The remaining current is how much? 75 minus I. Out of this, so what is the current injected by the source at P? It is I. Out of this I current, 10 ampere current is flowing through this load. Then what is the current that is flowing from point P to point R? Point P to point R. The current flowing is I minus 10 because already 10 ampere is tapped at this point. Now at point R, the load is tapping 20 ampere. So what is the current flowing through the branch connected between R and S? It is I minus 30. Now, how much current is being tapped at S? 30 ampere. So what will be the current that is flowing through the branch that is connected between S and Q? It will be I minus 60 ampere. So these are the currents that are flowing through the branches. Now if we calculate the voltage drop between point P and point Q on this distributor, what we are going to get? Vp minus Vq, that is equals to 5 volt is equals to, what is the current flowing through the branch PR? I minus 10, that is I minus 10 into, what is the resistance? 0.1 plus, what is the current flowing through the branch RS? I minus 30, I minus 30 into 0.15, and what is the current flowing through the branch connected between points S and Q? That is I minus 60, that is I minus 60 into 0.2. Okay, so if you simplify this, 5 volt is equals to 17.5, which implies 0.45 I is equals to 22.5. So from this, I value is how much? 22.5 divided by 0.45, 50 ampere. So how much current is flowing from the source at P? It is carrying 50 ampere. Then what is the current that is flowing from the source at Q? It is remaining current, that is 25 ampere. So what is the right option? The source at P is supplying 50 ampere. The source at Q is supplying 25 ampere. So option C is the right option. Insulator discs of identical capacitances make up a string of 22 kV 50 Hz single phase overhead line insulation system If the pin to earth capacitance is also C, then the string efficiency is. So first string efficiency formula we'll discuss. String efficiency is given by the formula voltage of conductor with respect to tower or ground, because the tower is grounded, divided by K into voltage across the disk next to conductor. Understand? So this is the formula for string efficiency. It is the ratio of voltage of the conductor with respect to tower or ground, that is phase to neutral voltage of the conductor, divided by K into voltage across the disk that is present next to the conductor. Where what is the K value? K is the number of disks in the insulator string. So K is the number of disks in the insulator string. String efficiency specifies the percentage utilization of the insulating material. Higher is the string efficiency, better is the utilization of insulating material in the string. So ideal value for string efficiency is 100%. Ideal value is 100%, which you can see in the HVDC lines. So in HVDC lines, the string efficiency is 100%. So string efficiency specifies the percentage utilization of the insulating material in the insulator string. Okay. Now, if you look at what is the given the problem, he has given that the voltage, it is a single phase transmission line. So what is the voltage of conductor? Voltage of the conductor with respect to ground is 22 kV. Now he is asking what is the string efficiency. To calculate string efficiency, what we have to calculate? We have to calculate even value. The string efficiency in this case will become 22 kV, because this is the voltage of conductor with respect to tower, into how many disks are there in the string? There are 2 disks. And what is the voltage across the disk adjacent or next to the conductor? That is E1 into 100. This will give you the string efficiency. Understand? So even here string efficiency is usually mentioned in percentages. So percentage string efficiency is given by this ratio. Okay. Now again, so let us assume the current, this current is I1, this current is I2, this is IC1. So by the KCL what we are having, I1 is equals to I2 plus IC1, since we have already done in the previous problem in directly rating. So what is the voltage of the conductor? This one value will become E1 divided by 1 by j omega C, and I2 current, that is the current flowing through the disk connected to cross arm, this will become E2 divided by 1 by j omega C. And what is the voltage of this point? The voltage at this point is E2 divided by 1 by j omega t. See, cross arm is this one. This is called cross arm. Okay. Next. So if you simplify this, what you are going to get? J omega C E1 is equals to j omega C E2 plus j omega C E2. If you fill j omega terms, you are going to get E1 is equals to 2 E2. But what we know, the voltage of the conductor, that is equals to 22 kV is equals to E1 plus E2, that is 22 is equals to E1, instead of E1 I am writing 2E2, 2E2 plus E2, that is 3E2. So from this E2 value will become, this value is 7.33 kV. So which implies E1 value will be how much? Twice of this one, 14.66 kilovolt. So we know both E1 and E2 values. Applying in the formula of string efficiency, what you are going to get? (22 divided by 2 into 14.66 into 100). This value will become 75%. So string efficiency for the given case is 75%. So which is the right option? B is the right option. The load current in the short circuit calculations are neglected. Why? Because short circuit currents are very much larger than the load currents. Short circuit currents are greatly out of phase with load currents. Which of the statement is correct? So while doing the fault analysis, short circuit analysis means fault analysis, we neglect load currents because load currents, when the system is operating in healthy condition, most of the times the load currents are mainly resistive. Load currents are mainly resistive because the normal operating power factors of the power system will be in the range of 0.8 to 0.9. So load currents are mainly resistive in nature. Understand? Okay. Second thing is, when fault occurs, the fault currents are almost inductive, because when you do fault analysis, you neglect the resistance of most of the power system elements like generators, transformers, transmission lines. So fault currents are almost purely inductive currents. So what is the phase angle between the resistive currents and inductive currents? 90 degrees. So short circuit currents are greatly out of phase with load currents. This is true. Second point, the load impedance is very much greater than the system impedance. That means the load impedance value is very much greater than the system impedance, because the impedance of all the power system elements like alternators, transformers, transmission lines is very small when compared to the load impedance. So fault currents are very much greater than full load currents. So to simplify the fault analysis, we neglect the full load currents in fault analysis. So even this is true. So short circuit currents, that is fault currents, are much larger than the load currents, and short circuit currents are greatly out of phase with load currents. Both the statements are correct. Because of these two reasons, mostly to simplify the analysis, we neglect the load currents in short circuit analysis. So which is the right option? D is the right option in this case. The next question is, the direct axis reactance XD of a synchronous generator is 0.4 per unit based on the generator's nameplate rating of 10 kV and 75 MVA. The base for the calculation is 11 kV and 100 kVA. What is the per unit on the new base? What is telling? The direct axis reactance of generator is 0.4 per unit on 10 kV base voltage and 75 MVA base MVA. Now he wants you to calculate the per unit value of the same synchronous generator on a base of, what is the new base values? 11 kV and 100 MVA. So you have to calculate the per unit value on a different base value. So what is the formula? Z per unit new is equals to Z per unit old into new base MVA divided by old base MVA into old base kV by new base kV whole square. So this is the formula which we use to convert the per unit value from one base to other base. Z per unit new is equals to Z per unit old into new base MVA by old base MVA into old base kV by new base kV whole square. So in this question, what is this value? This is 0.4. What is the new base value on which we are calculating? 100 MVA. Old base MVA is 75. Old base kV is 10 kV divided by 11 kV whole square. So this value will become how much? 0.44 per unit. So D is the right. A delta star transformer has face-to-face voltage ratio of K. The line-to-line voltage ratio of star delta connection is given by. So in this question, what he's telling, neglecting the phase shifts in this connection, he's only speaking about the transformation ratio. Let the phase voltage across the delta winding is X volt. Let the phase voltage across the star connected winding is Y volt. Now what he's telling in the given question, K is equals to delta phase voltage is X divided by star phase voltage is Y. Okay. Now he is asking what is the line to line voltage ratio of star delta connection of the same. So in this case, in the star connected side, what is the line to line voltage? Line to line voltage in star connected side is root 3 times. The line to line voltage is root 3 into Y into root 3 into Y, because it is root 3 times the phase voltage. What is the line to line voltage in the delta? The line to line voltage and phase to neutral voltage in delta is same. So if you calculate this ratio of, so now if you calculate the line to line voltage of star side divided by line to line voltage of delta side, what you are going to get? So what is the line to line voltage on star side? How we can write? Root 3 into Y. And what is the line to line voltage on delta side? That is X. Now this value will become how much? Root 3 into the ratio of X by Y is K. The ratio of Y by X will become what? 1 by K. So the answer is root 3 by K. D is the right option for the given question. So coming to the last question in this lecture. So he is telling, in a 3 insulator string, voltage across the lowest unit is 7.5 kV. The string efficiency is 84.28%. The total voltage across the string will be equal to. So he is asking what is the total voltage across the string. So what he is telling, the voltage across the last disk is 17.5 kV. That is voltage across the disk that is connected to the conductor is 17.5 kV. Now he wants us to calculate the total voltage between the cross arm and the conductor, that is the total voltage of the string, that is voltage of the conductor with respect to tower. Understand? So if you apply the string efficiency formula, string efficiency is given by voltage of the conductor with respect to tower or neutral divided by how many discs are there in the string? 3 into what is the voltage across the disc that is next to the conductor? 17.5 into 100. This value is how much he has given? 84.28. 84.28 percentage. So from this we need to calculate VC value. So VC value will become 0.8428 into 3 into 17.5. This will be the voltage of the conductor from this one, whose value boils down to 44.25 kV. So option B is the right option. Okay. So he has given, in this problem he has given string efficiency. Now he is asking us to calculate the voltage of the conductor with respect to tower, whose value is 44.25 kV. Thank you.